The interconversion between the alpha and the beta forms of a monosaccharide actually represents one of the most basic reactions that sugars undergo. And this is a reaction called mutarotation. Basically, all it does is it interconverts the alpha and the beta forms of two monosaccharides. So if we look at glucose, for example, if we put glucose into an aqueous solution, we will find that about a third of it winds up in the alpha form, about two-thirds of it in the beta form. So that indicates that the beta form is a little bit more stable. Once again, because it has all of its hydroxyl groups on equatorial positions, as opposed to the alpha form, where the anomeric carbon is going to have its hydroxyl group on an axial position. So if we mutarotation is so equilibrium controlled that if we were to actually take glucose and put it all into the beta form and isolate it as the beta form, once we put that into water, it's immediately going to form this mixture of two-thirds of it being beta, one-third of it being alpha. Now, there are a variety of other reactions that carbohydrates undergo, and I'm going to kind of go through them somewhat quickly, just because they're not the most important things. I'll tell you, if a reaction is important, but basically most of them are important because the importance of reactions is that they make a lot of derivatives of monosaccharides. So, for example, glucose, as we see right here, it can undergo an oxidation reaction, or it can actually go a number of different oxidation reactions. For example, the most common one that we see is the oxidation of carbon number 6 to the corresponding carboxylic acid. This gives rise to a molecule called glucuronic acid. And glucuronic acid is actually important for basically building our joints. In fact, we basically can take derivatives of glucuronic acid as a mechanism to prevent joint damage, which I'll show you the structure of that, and we'll talk a little bit about it later. Glucuronic acid can be further oxidized. The aldehyde can be oxidized to the corresponding carboxylic acid, and this gives rise to a molecule called glucaric acid. Likewise, if we take glucose and oxidize the aldehyde to the corresponding carboxylic acid, we form gluconic acid. And the most common reaction that we see is the oxidation to form glucuronic acid, and this shows the negatively charged form of glucuronic acid, which is what it would exist at physiological pH. Basically, this would be alpha glucuronate, indicating that it's glucuronic acid in its deprotonated form, and of course the alpha indicating the orientation of the hydroxyl group on this anomeric carbon. So this would be the Howard projection that would very commonly be seen from the formation of glucuronic acid. Now, just like we can have a cyclization reaction that occurs between an aldehyde and a ketone, or an aldehyde and a hydroxyl group, or a ketone and a hydroxyl group, the same thing can happen with a carboxylic acid and a hydroxyl group. If you think about the formation of an ester, the formation of an ester is carboxylic acid plus alcohol. Well, we can form a cyclic ester known as a lactone if we have a carboxylic acid and an alcohol. So if we oxidize a carbohydrate, for example, to glucuronic acid, as we see over here, glucuronic acid can actually undergo a cyclization basically by reaction of the hydroxyl on carbon 2 with the carboxylic acid. And this would be glucurano delta lactone. Basically, there's our newly formed ester right here. This oxygen came from carbon number 2. And then here's our aldehyde that's still present in the molecule. Anyways, the formation of lactones does happen. I mean, vitamin C is actually a great example. The formation of vitamin C requires the formation of a lactone in its synthesis. And I completely forgot I had the slide of vitamin C right here. So basically, we as humans require the dietary intake of vitamin C. And that's basically because we lack an enzyme called gulonolactone oxidase. And basically, this is the step catalyzed by gulonolactone oxidase. What happens is that glucose gets converted, D-glucose specifically, gets converted into L-galactose, as we see here, which then undergoes oxidation to form this galactonolactone. And then the last step in this is what we as humans and other primates cannot do, which is basically convert or oxidize this lactone to the form that we see here, which is the active form of vitamin C. So basically, some animals have the ability to do this. There are multiple ways to get to ascorbic acid, vitamin C. This one in particular is commonly seen in plants. Animals do have the capability of, most animals do have the capability of synthesizing vitamin C, and they use a slightly different route to do it. But ultimately, it all gets to the same endpoint, making the ascorbic acid, which is a very effective antioxidant in our body. In addition to oxidation, we can also reduce monosaccharides. For example, glucose very often gets, we can reduce it to sorbitol. It can be done in natural systems using the enzyme aldose reductase, as we see right here. Basically, aldose reductase uses NADPH. This is a source of electrons to convert the aldehyde into the corresponding alcohol, which unfortunately this is not showing up as the corresponding alcohol. This should be CH2OH. This molecule is known as sorbitol, very common ingredient in things that you want to preserve by having water associated with it. So chewing gum, very often, in order to hold on to the small amount of water that's in chewing gum and it basically doesn't become desiccated, sorbitol will be added. Generally, sorbitol is made in an industrial situation using hydrogen and a nickel catalyst, relatively high pressure hydrogen. Basically, you simply take glucose, you reduce it to sorbitol, and then you've got all sorts of sorbitol to add to whatever products you feel are enhanced by adding sorbitol to it. Isomerization is obviously a very important kind of reaction. For example, the conversion of glucose into fructose. Basically, in this case, the carbonyl group is on carbon 1 in glucose. We're going to move that to carbon number 2. We will look at this isomerization in quite a bit of detail when we talk about glycolysis, because the conversion or the breakdown of glucose into simpler molecules requires that it get isomerized into a derivative of fructose, and we will see that process take place. So very common isomerization, conversion of an aldose into a ketose. We can also do isomerizations at a stereocenter. So for example, here we have glucose with the hydroxyl on the right-hand side at carbon 2. Here we have mannose with the hydroxyl on the left-hand side at carbon 2. So the conversion of glucose into mannose would be referred to as an epimerization, because we're making the epimer, the C2 epimer of glucose, and thus it falls under the category of an isomerization reaction. So with all the hydroxyl groups we have around, it makes sense that very often we stick things to those hydroxyl groups and make esters. Some very common esters to make are phosphate esters, as is seen in this structure here. Here we have a phosphate attached to carbon number 6. This is glucose 6-phosphate. Same thing can happen with sulfate esters. Here we have glucose 6-sulfate. Glucose 6-phosphate is actually used as an intermediate in a variety of biochemical pathways. We actually see it in glycolysis. It's also used as an input into making glycogen. Glucose 6-sulfate, on the other hand, is used very commonly in connective tissue. So things like ligaments or cartilage basically use derivatives of glucose 6 sulfate. The sulfate is there to play a very important role to make to basically attract water to this molecule. Other derivatives that we often find, amino sugars. In this case, basically we have taken a hydroxyl group and replaced it with an amine group. This gives rise to a molecule called glucosamine if it's simply an NH2 there. Or we can very often attach an acetyl group, which basically the R there would look like this, where here's our point of attachment, and then we've got double bond to oxygen there. Basically, both of these molecules, glucosamine and acetylglucosamine, once again, are very important for proper cartilage formation. We can also reduce sugars and basically remove the hydroxyl group. This gives rise to the deoxy sugars that are critical for making our deoxyribonucleic acid, or DNA. So the last thing I want to look at here with regard to reaction before we kind of go on to look at some more complex structure is the reaction that actually allows us to make, to start putting monosaccharides together to make larger molecules. And this is what's called glycoside formation. And basically we're going to take a sugar molecule, and a monosaccharide, and react it with another alcohol. What that does is basically, for example, here's the alcohol we're adding. We're going to add that to the anomeric carbon, and we're going to end up with the OR from our alcohol. And a couple things that does. First of all, without the hydroxyl group, now we've essentially converted that hydroxyl group into, or changed the hydrogen for an alkyl group. This is no longer able to undergo mutarotation, basically, and whatever we're stuck with, if it's an alpha anomer or beta anomer, we're stuck with that. Also, it prevents oxidation of the anomeric carbon. When we simply have this hydroxyl group here, this hydroxyl group is going back and forth between being the hydroxyl group and being the carbonyl group, the aldehyde in this case. And aldehydes are prone to oxidation, whereas the hemiacetal that we see is not. If we go over here and basically lock that molecule in as as what we call a pyranoside, it is no longer capable of going back to forming the carbonyl group, so it is not capable of being oxidized. So when we do this reaction, we do a couple of things. We prevent mutarotation and we prevent oxidation of our monosaccharides.